Hello, and welcome to Linear Algebra. This is Lecture 9, and today's topic is matrix multiplication. So last time, we talked about how the space of linear maps between V and W is itself a vector space. And we talked about how the linear maps between Fn and Fm, for any field F, is isomorphic to the space of matrices of size m by n. Okay, so far, matrices form a vector space. We know how to add them and how to multiply by a scalar. On the other hand, here we've shown that it's isomorphic to linear maps. In linear maps, we also know how to compose them. So what we want to do is take the composition of linear maps and use that to define a product on matrices. So this time, we'll talk about multiplying matrices. Okay, so if S is a linear map between Fn and Fm, and T is a linear map between Fp and Fn, then it makes sense to compose the linear maps, and we'd end up with a linear map between Fp and Fm. Right, because if you give me a vector in Fp, then I can use T to get a vector in Fn, and then I can use S to go from Fn to Fm, and so I end up with a vector in Fm. On the other hand, each of these linear maps is given by multiplication by some matrix. Okay, so if A, right, let's give it a size. This would be a matrix of size m by n. Is the matrix associated to S, and B, size n by p, is the matrix associated to T, then we define the product of A with B to be the matrix associated to S composed with T. And this is the way matrix multiplication was originally defined by Arthur Cayley, as we talked about some other class. Okay, so specifically, or said again, that is A times B, so this would be a matrix of size m by p, is the matrix satisfying that A times B multiplying the vector V is equal to A multiplying the vector that you get by doing B multiplying the vector V. Right, this is for every vector v in F to P. Right? Note the dimensions. Okay, so in order to compose these maps, the only reason this makes sense is that T ends up in Fn and S starts in Fn. Right? So here, the way this works out in matrix multiplication is that if I have A and B, so this has size m by n, and B has size n by p, right? So what you need is for the dimensions on the inside, the dimensions that are next to each other, to match. And if they do match, then they sort of cancel out, and you end up with m by p. Okay. So now there are many ways of thinking about A times B, and all of these ways are useful. So first, let's look at the columns, right? So the jth column of A times B. Okay, so anytime we're looking at the matrix associated to a linear map from Fn to Fm, we know how to find the columns of that matrix just by evaluating on the standard basis, right? So on the vectors Ej. So the jth column of AB is AB multiplying the vector Ej, right? And that is A times B of Ej, right? But this, by the same reasoning, this is the jth column of the matrix B. So if we write B as, if we denote the columns of B as being lowercase b1 through lowercase bn, then A times B is the matrix whose columns are A times lowercase b1 up through, oh, sorry, B has P columns, all the way through A times lowercase b P. Now remember that matrix vector multiplication is take a linear combination of the columns of the matrix where the coefficients are the coordinates of the vector. So from here, we see that in particular, every column of A times B is a linear combination of the columns of A, right? So the first column of A times B is the linear combination of the columns of A, where you use the entries of B1 as the coefficients, and so on with all of the other columns. Okay, so that's the first way of thinking about this matrix-matrix product. Directly from this one, we get our second way. So this expression gives us a formula for the individual entries of A times B, right? So if I look at the ijth entry of AB, right? So this, remember, is I tells us what row we're on, J tells us what column we're on. So that means that this is going to be the ith entry in the vector A times Bj. right? Okay, but that means that you're going to take the sum of AIK and then BKJ. K goes from 1 to n. Okay, so notice that this makes sense because the second index for the entries of A matches the first index of the entries for B, and so it makes sense to sum over that index. Okay, so this gives us a formula for the individual entries. Okay, now, of course, we can think of this as like a dot product, right? This would be like the dot product of the ith row of A with the jth column of B, right? So, but notice that dot product is itself a matrix product. It's just very specific matrices, specific sizes of matrices. So let's call a matrix of size 1 by m for any m, a row vector, just like a column vector of size n is the same as a matrix of size n by 1. So now, if V is a matrix of size 1 by n, so a row vector of size n, and W is a matrix of size m by 1, I guess if we're thinking of them as matrices, I don't need to put bars on them. So it is a column vector of size m, then VW, the matrix product, makes sense when n is equal to m, right? Because I need the interior indices to match. And if they do, then they cancel, right, when you do the product, and you're just left with a 1 by 1 matrix. So it's a matrix of size 1 by 1, right, which is the same as just an element of F, right? Okay, and if I write V as V1 through Vn like that, and W as W1 through Wn like this, then this matrix product is just a single element of F, and that is the dot product. What we call the dot product in calculus. Okay, now comparing formulas, we see that the ijth entry of AB is the matrix product of the ith row of A and the jth column of B. Right, so if I write A as the matrix whose rows are A1 through AM, and I write B as the matrix whose columns are B1 through BP, then A times B has entries A1 times B1 through A1 times B P, and then a MB1 all the way through a MBP, where these are matrix-matrix products, or if you prefer, dot products. Okay, now I like to think of this, a way to remember how you do this. It's when you're naming a matrix, you go down and then to the right. And when you're multiplying, you go to the right and then down. So it's like there's two halves of a square. One half you use for naming, the other half you use for multiplying. Okay, and now finally, so we've done thinking of matrix-matrix product by looking at the columns. We've done thinking of matrix-matrix product by looking at the individual elements. So now we want to think of matrix-matrix product by looking at the rows. Okay, so a third way to think about matrix multiplication is to focus on the rows instead of the columns. So let's do that. So if we write A as the matrix whose rows are A1 through AM, then A times B, right, has first row equal to A1 times B in that order, and mth row AM times B in that order, right? So that is the jth row of A times B is the product of the jth row of A with B. Okay, so those are three ways to think about matrix-matrix products, and they're each useful at different times. Let's do an example. So let's look at the matrix A, 0, 1, 2, 3. Right, so a square 2 by 2 matrix. Let's look at B, the matrix -1, 1, 2, -2, and 0, 4. Okay, so then A times B, okay, well, let's look at the sizes first. This is a 2 by 2. This is a 2 by 3, right? So the inner indices match. So that means the product is defined. And we're going to get a matrix of size whatever's left over. So a 2 by 3 matrix, so same size as B, right? Okay, and now to find each entry, we do this row times this column, right? And that gives us the first entry. Then we do this row times this column, and that gives us the second entry. Then we do this row times this column, and that gives us the third entry. Now, when we go down to the second row of AB, we start using the second row of A. So we find this row times this column gives us 1. Then this row times this column gives us -2. And then finally, this row times this column gives us 12. Okay, so there we go. That's how you find this one. Notice that B times A is not defined. Okay, so it doesn't make any sense to multiply them in this order, right? Because the indices wouldn't match. This is a 2 by 3 and this is a 2 by 2. And so the interior indices don't match. We have a 3 and a 2. Right, so just like for linear transformations, that's one way of seeing quickly that matrix multiplication is not commutative. So then it's entirely possible that A times B makes sense, but B times A does not make sense. So it definitely is not equal to A times B. But that's not the only way that can fail. So notice that if I take A to be the matrix 0, 1, 0, 0, and I take B to be the matrix 0, 0, 2, 0, then I'll let you check that A times B gives me 2, 0, 0, 0, and B times A is 0, 0, 0, 2. So here, A times B and B times A make sense, but they're not equal to each other. Right? So matrix multiplication is not commutative. It's very important. Okay, great. So here's another operation that's useful for matrices. This is something we'll come back to later in the course. This will be very useful, but this is a good time to introduce it. So given any matrix, so m by n matrix with coefficients in a field, let's say that A has entries aij, where I goes from 1 to m and j goes from 1 to n, then we define the transpose of A is the matrix A upper T of size n by m. So notice that here we had m by n, and here we're going to have n by m. So we're switching the two indices. And that's how you find the entry. So the ijth entry of A transpose is the jith entry of A. So for all I between 1 and m and j between 1 and n. Right, so another way of saying that is that if A is the matrix whose rows are A1 through AM, then A transpose is the matrix whose columns are A1 transpose through AM transpose. Right, so you just take the rows and you make them columns. Now note that if I transpose a matrix and then I transpose it again, I just get back the matrix I started with. Right, and that's really easy to see. You've just taken the rows, made them columns, and then made them rows again. Right? Also true, but takes a little longer to see perhaps, is that if I transpose a product, AB transpose, I get B transpose, A transpose. Okay, so I'll let you check this. It's a nice exercise in manipulating the formula for the ijth term in the product matrix. So go ahead and work that out and check that you get the same ijth term on both sides of this equality. Okay, now that makes sense for any field. If the field you're working with is the complex numbers, then there is a special version of the transpose or a modification of it that is very useful. Well, before I say that, let me give you one instance of why you might want to do use a transpose. So just looking at how this transpose turns a row vector into a column vector and vice versa, right? If V and W are two elements of Fn, then their dot product is, let's say, is the matrix product W transpose V, right? So W transpose. So if you think of vectors as being column matrices, then by taking the transpose, I've turned this column matrix into a row matrix, and now I do the product of these matrices, and I get back a number. So that's one reason why you might want to have transposes. We'll see other reasons later. Right, but now let me mention that if the field is the complex numbers, then we also use the adjoint or conjugate transpose. So if B is an n by n matrix with complex entries, then B star is the n by m matrix with complex entries, where the ijth entry of B star is little b j I complex conjugate. So that's why it's conjugate transpose. So you transpose, you change the order of the indices, and then you take a complex conjugate. So for example, if B is the matrix with entries I, 7 minus 1/2 I, 2 plus 3 I, and 5, then the adjoint, or the conjugate transpose, would be, okay, so first I'm going to take the first row, and I'm going to make it the first column, but I'm going to have to conjugate. So I'm going to put 2 bar and 2 plus 3i bar. And then the second row becomes the second column, 7 minus 1/2 I. But I need to conjugate, so I put a bar on top of them. And now let's actually do the conjugate. Remember that a complex conjugate just changes the sign of the imaginary part. So I becomes minus I, 2 plus 3i becomes 2 minus 3i, 7 minus 1/2 I becomes 7 plus 1/2 I, and 5 just remains 5. So there you go. That is the conjugate transpose of this matrix. Okay. Very good. So those are two operations on matrices. Right. Let me mention here also, if the product makes sense, then so I'll just say here similarly to the transpose, if you take a matrix and you take its adjoint and then its adjoint again, you get back the matrix you started with. And if you do a product of two matrices and you take the adjoint, then you get the product of the adjoints, but in the opposite order. Okay. Here's another operation that you can do sometimes. So we say that a matrix A of size n by n, so only for square matrices, is invertible if there is a matrix B, also of size n by n, such that A times B is equal to the identity matrix of size n by n, and that's equal to B times A. In which case we say that B is an inverse of A. Okay, so you might be thinking, why do we say is an inverse? Shouldn't we be saying that it is the inverse? Well, yes, but we have to justify that, right? That is a non-trivial fact. If A is invertible, then it only has one inverse. Okay, so it's non-trivial, but it's not very hard. It's very similar to properties that we saw when we were looking at the arithmetic of fields. Right? So, of course, notice that matrices do not form a field because there are, we'll see, non-zero matrices that are not invertible. But if you do have an invertible matrix, and if B1 and B2 are both inverses of A, then what you can do is start with B1. So B1 is the same as B1 times the identity, right? Multiplying by the identity doesn't change anything. How do we know that? Well, the identity is the matrix associated to the identity linear map. And composition with the identity linear map doesn't change anything. So multiplication by the identity doesn't change anything. Of course, you can also just check the formula for the ijth entry of B is the same as the formula for the ijth entry of B times the identity. But in any case, it doesn't change anything. So I can write B1 as B1 times the identity. Now, because B2 is an inverse of A, I can write the identity as A times B2. Now, because composition of linear maps is associative, matrix multiplication is associative. So I can write this as the product of B1 times A times B2. But B1 is an inverse of A. So this is equal to IN times B2, and that's equal to B2. Right? So if A were to have two inverses, then actually they would be equal to each other. So A only has one inverse, if it has any. So thus we can use the notation A to the minus 1 for the inverse of A when it exists. Right? So because it's an ambiguous, it only depends on A, then we might as well write it as A inverse, A to the minus 1. Okay, invertible matrices are nice to have, for example, for solving systems of linear equations. If A is invertible, then it is easy to solve AX equal to B. The solution is X equals A inverse times B. Okay. If A is invertible, if A and B are invertible, so let's say that I have two matrices of size n by n, and they're both invertible, then so is their product, right? Which again is an n by n matrix. In fact, we can just write down a formula for the inverse of the product. It's B inverse times A inverse. Okay. Remember that matrix multiplication does not commute, so the order is important, right? So as a quick exercise, check that the inverse of A times B is B inverse times A inverse, right? It's not A inverse times B inverse unless A times B commute. A and B commute. Also, by the uniqueness, note that if I take the inverse of A and then I take the inverse of that, I get A again. Right? Another way of saying that is that if A is the inverse, if A is the inverse of B, then B is the inverse of A. Okay. Here's an easy example. Suppose I give you 4 elements of a field, and they are such that A times D is not equal to BC. Then the matrix ABCD is invertible And so take AD minus BC inverse and multiply the matrix D minus B minus C A. This is its inverse. Okay, so I'll let you check that. But to check that, notice that all you have to do is multiply these matrices together and see that you get the identity no matter which order you do the multiplication. Finally, let me give you an example of a non-zero matrix that is not invertible. Right, so take the matrix A, 0, 1, 0, 0. Right? This is a 2 by 2 matrix, and in any field, right? Because every field has the numbers 0 and 1. So this makes sense no matter what field you're working with. This is not invertible. Right? So how do we know that? Well, notice that A squared is equal to 0, 0, 0, 0. Right? The zero matrix. So this is not invertible, right? No matter what you multiply, the zero matrix is going to get you back to zero matrix. So there's no way that A squared has an inverse. There's no way the multiplication is going to give you the identity matrix. And if A were invertible, then A squared would also be invertible. Right, so A cannot be invertible no matter what field we're working with. Okay, so that shows that matrices with matrix addition and matrix multiplication do not form a field, right? Because remember, in a field, every non-zero element has a multiplicative inverse. Okay, we'll stop there for today and pick it up there next time.